Alright, so here is a two-dimensional collision. Alright, if it's a collision, then that means that we're going to probably use the conservation of momentum, right? So we've got m1 moving in at v1 initial, and m2 moving this way at v2 initial, and they're going to have this sort of glancing blow. They're both moving horizontally in the first place, but then they hit each other sort of cockeyed, and they shoot off like this. M1 goes off this way, and we know this v1 initial, and we know the angle it goes off to. What we want to find out is what will v2 be right here? What will this final velocity be? And we want to know at what angle it gets shot away. Let's say this angle right here, and I'll call it phi. So we're looking for these two things. We know the masses, we know their initial speeds, velocities, and we know the final velocity of mass 1. Alright, so this problem is really going to show the fact that momentum is a vector and actually use that. So let's write out the conservation of momentum. Momentum final equals momentum initial, like so. But what this means is that in the vector form can be written this way, that momentum x final equals momentum x initial, and momentum y final equals momentum y initial. Okay, so not only is momentum conserved, but as a vector, it's conserved in both the x and y directions. Speaking of which, I should have my x and y axis on this picture. Okay, so we'll go with the usual convention on that, the direction of the x and y axis. Okay, so let's continue solving here. How about we start with excuse me, the x direction. So this says basically, well, it's just conservation. So initially we had momentum 1. Let's skip that. Let's look at their initial velocities are horizontal. So initially these velocities are, the momentum are completely in the x direction. Okay, so I'm going to go right to mv here because that's momentum. So initially the horizontal momentum for mass 1 is m1 v1 initial, and the horizontal initial momentum for mass 2 is going to be negative m2 v2 initial. Now that's because its velocity is pointing in the negative direction. Alright, now in the end here, well, we want to have the x component of final momentum for each piece. I'm going to move this over. We'll have to move down for the y momentum. Okay, so that was my, let me rearrange this a bit here. Alright, so we're working on momentum in the x direction. So at the end, well, momentum is, it's diagonal, or in other words, it has both x and y components, right? But I can just break it up like we always do with velocities. So this would be v1y, v1x. This would be v2x, v2y. All right. So then my final momentum in the x direction, is going to be, well, m1 times v1x minus m2 times v2x, right? Because again, mass 2's x velocity is in the negative direction there. Okay, so looking at this equation, well, I made a bunch of variables up just now, but we know that v1x is going to be equal to v1 cosine of theta, and v1y is going to be equal to v1 sine of theta. All right, so we know theta and we know v1, so this gets us somewhere, plugging these in instead. So I can rewrite this. So we have m1, that's v1 cosine theta. Now I don't know this v2x, so I'll just leave it. Okay, so my only unknown in here is v2x. So that's not exactly what I was looking for, but maybe my momentum in the y direction can solve v2y for me. If that was the case, then at the end we could do this. right? And that. Okay, well, my handwriting. v2y over v2x there. Okay, so remember this stuff, it's vectors, keeps coming back, right? Okay, so I guess I should just go ahead and, no, forget it, it's just algebra. So you solve this for v2x, okay? And we know everything here except for v2x, all right? And now here, conservation of momentum in the y direction, well, I can take similar steps, right? But initially, there's actually no momentum in the y direction, right? There's no velocity in the y direction on either mass. So initially, we have 0 momentum in the y direction. But in the end, we do have some. We've got m1 v1y in the positive direction, but then minus m2 v2y, because as you can see, v2y is pointing down in the negative direction. Okay, and we know that I can rewrite v1y as v1 sine of theta, and I'll rearrange a little bit while I'm at it. Okay, just adding over the m2 v2y. And so now if we solve this, which of course will be just one step, solve this for v2y, then we'll have our components, basically. We'll have the velocity components of m2 in the end, final velocity of m2 components. So then we can take those components and find the actual magnitude of velocity v2, and we can find the angle. All right, so these ones are a little bit unpleasant just because vectors can be tedious, but our conservation of momentum statement here simply breaks into x and y pieces, and we just solve them like any collision. And unfortunately, that does involve often breaking these diagonal velocity vectors into their horizontal and vertical components, or their x and y components. And that's it. Well, kind of. I'll let you do the last steps. I didn't give you numbers anyways.